Hey everyone, thanks for making it out to the last possible session on the last day of VMworld. I appreciate you guys coming here. As you can tell from my voice, I've had a long several days, and I'm sure you guys all have, so I'll endeavor to provide you with some useful content and a couple of cool demos. I'm Vivek Saraswat. I'm a product manager here at the storage availability team in VMware. My focus is on storage for cloud-native applications. And today I'll be talking to you about containers without compromise, persistent storage for Docker containers with VMware. So to begin, as you've probably seen several times this week, just a disclaimer, this may contain product features that are currently under development. And this represents no commitment from VMware to deliver these products into a generally available product. Features are subject to change, technical feasibility and market demand, pricing and patching, et cetera, et cetera. So just keeping that all in mind. And a quick agenda of what we're going to cover today. So we'll begin with a quick introduction to cloud-native applications, a little bit of a 101 on containers, moving to talking about persistent data in containers, what are some of the use cases, what's some of the philosophy. We'll talk about some of the VMware solutions and partner solutions for cloud-native storage. And we'll end with this section with a sneak peek towards what we're doing in the future of software-defined storage for cloud-native applications. So what are cloud-native apps? If some of you have been to the other tracks, you may have seen slides similar to this. What we've learned is that there's really not one definition for what a cloud-native application is, but there's a series of traits that are consistent across most cloud-native applications. But in general, you can think of this as next-generation applications built for web-scale use cases, social, mobile, analytics, cloud, et cetera. So we're talking billions of users, hundreds of millions of users, tons of data. So what are some of the characteristics that involve a cloud-native app? The first we've seen is a huge increase in focus on the developers, and in particular, developer access via APIs. You might have heard of the infrastructure as code movement. This is the ability for developers to directly provision their infrastructure from their code through APIs and through CLI. So providing this access is extremely important. And from our perspective, VMware would like to reach out more to developers and make them a first-class citizen of the data center. Continuous integration and deployment. Cloud-native applications often move a little bit away from the waterfall methodology of development, where you do planning, development, testing, and release to customer over long periods of time. Instead, you're seeing quicker and quicker iterations. You're seeing people deploying monthly, weekly, daily, sometimes hourly or less. And this requires much more coordination between the developers and between the operations and IT folks, hence the term DevOps. And so that's why continuous integration and deployment is so important. Cloud-native apps are built for scale. As we talked about, hundreds of millions, possibly even billions of users. This means you need to have distributed applications across multiple clouds. It means that your storage may need to go into the petabyte level for individual applications alone. App-defined availability. So in a typical VM-centric world, the hypervisor defines things like high availability for a VM and tries to keep them alive and tries to maintain parity on the compute side. However, we found that in the cloud-native world, it's really the application has to be written to define its own availability. And I'll explain some of this in some later slides. Microservices, not monolithic stacks. Cloud-native applications move away from having a single monolithic platform which contains all of the necessary elements for a piece of software. Instead, you have these individual independent microservices that are loosely coupled and tightly integrated that speak to each other via RESTful API. And that means with each microservice, you can use them modularly for multiple applications, and you can swap them out and update them as necessary independently. And finally, decoupled from infrastructure. Cloud-native means that a developer should be able to run their app anywhere on any cloud. And this is where the promise of containers come in, and I'll talk a little bit more about that. But the idea is, as long as you're sitting upon the correct OS, you shouldn't care whether you're running somewhere in the public cloud or on a private cloud deployment. So what exactly are containers? Just a quick show of hands. How many people are familiar with containers in the audience? Pretty much all of you. OK, so this will be a pretty quick overview. How many are actually playing around with containers in their deployments? OK, a very good number of you. So again, just as a quick overview, what is a container? If we think of a VM as OS-level isolation, as a guest OS with several applications sitting within it, a container is really app-level isolation. It's isolation just for the application and its necessary binaries and libraries. And this isolation allows you to provide individual kernel subsystem isolation as well. So things like isolating the file system, CPU resources, memory resources, networking resources. Being able to do that fine-grained isolation at an app level. And then using some sort of user-level process like LXC or for Docker libcontainer in order to orchestrate these subsystems and create an entire container. Now, containers are not new. This is something that has existed for many years, whether through Solaris zones, FreeBSD jails, but they've really become popularized with Docker today, and we'll talk a little bit about why that is. But what makes containers so helpful? It's the ability to have this process isolation at an application level and not at a VM level. It's also about being able to create a reproducible environment. So instead of having to reconfigure each of your VM systems for each individual application stack, you can package it within a nice container and then send it to any VM or physical environment that needs to run that. And this really allows you to enable your application development and management at a really large scale. So how does Docker help with this? You can think of Docker as a shipping container for code. So developers love Docker because it allows them to do frictionless deployment and maximum portability. You create an app, you say Docker build my app. Once you've built that app into a container, you can push it to a public registry or a private registry in your cloud. And then anytime you want to use that app, you just pull it right back and run it. And you can make additional changes that layer on top of that app and then build a new container out of it. It's very simple and easy to use, and that's why people love Docker. It's because of this ability to have a very simple to use API that all your developers can use naturally, and it fits pretty well within your data center. So this is a really natural fit for the third platform world and for so-called 12-factor apps, microservices. It really makes the whole DevOps process that much easier. So now here's a distinction as to, we're going to start getting into stateless versus stateful. As you start bringing storage into your applications and your containers, what are some of the issues you deal with? This is an analogy we've probably heard several times before. I found this picture from the CERN website. I really like it. So it's the cattle versus pets analogy. Are people familiar with this? Cattle versus pets, show of hands. Quick. I see some nodding. OK. So in a pet's world, pet VMs are given a name like Puss in Boots, something that's very unique. They're very lovingly hand-raised and cared for. When a pet VM gets ill, you do everything you can to nurse it back to health, whether it's things like high availability, fault tolerance. You really want to keep that VM alive. Cattle VMs and by extension containers are a little different. They're very impersonal. They look almost identical to each other. They have a name like VM42, VM55. And when one gets ill, you don't try to protect it. You remove it and restart a new container or a new VM that contains the same information. Now, this makes a lot of sense for a stateless application. When you delete an app and you start a new one, you don't really care what's happening to the data. But what happens when you actually do care about your data? I love this picture. If you start a new container and you have stateful data, say it's a user configuration, database transactions, customer records, you might lose all of that data as soon as you start a new container. So you know that you're in a 12-factor cloud-native world. Your stateful data really needs to be accessed and protected separately from your stateless data. So the original model when Docker was becoming popular was to persist all of your stateful data to some non-containerized managed storage, such as an object store or a database as a service. But there are some issues with this. First of all, you have to re-architect your app in a way such that you have no local control over storage management. You're not writing to a local file system anymore, which a lot of developers may prefer. You have to build RESTful API gets and puts to an external service. You might end up with latency and access issues, right, when you're no longer running against local storage. And you might also run into issues at scale. You can imagine with containers, people talk about running thousands, tens of thousands, hundreds of thousands, millions of containers in a compute cluster. How do you make sure that your storage is able to keep up with your compute? So if you have a separate storage cluster, then it might not be able to scale at the same rate that's necessary as your compute. So these are some of the issues that arise when you're dealing with external storage management. And why is this really important now? It's because interest in containerized storage apps is really increasing. So the picture on the left here is from Docker's official repository. And you'll notice that some containerized stateful applications like Redis, MySQL, and MongoDB are front and center on the page. So clearly, this is something that at least shows visible interest on the Docker side. Now, if you go to their search bar and you type something like DB or database, I have 2,000 results here. If you change it slightly and say DB instead of database, you'll probably get another 1,000 or 2,000 results. So there's thousands of DB apps. And importantly, if you look at some of the download counts, it's a little hard to see here, but Redis has something like 6.3 million downloads. MySQL has 5.9 million. These are all in the millions of downloads, and this is old data already. So while this may not be an indication of what's running in production, it's clear that people have a strong interest in making containerized databases and containerized storage applications working. So what do you need to do in order to make containerized storage work on a local level? Well, this is where we bring in container data volumes. So you can think of this in many ways as a virtual disk for containers, if that analogy makes sense. Container data volumes contain all the persistent data for local containers. They appear as a directory within the file system of the host. Remember that a container sits on top of the host OS, so this just appears as a directory in that file system. And you can create it using a Docker API. You say docker run, -v is the command that creates a volume, and then you just point it to a directory that's your mount point. And this could be a local storage on the host, or it could be stored on external storage. And this is something that's really come up only fairly recently with the Docker API. And the benefits of this is that you can manage and preserve your stateful data in the volumes completely separately from the actual stateless containers. And you can also start utilizing the data services on your storage platform inside of these data volumes. So volumes really open up a lot of new possibilities for containerized applications. It is early days right now. The volume API it was experimental until not very long ago. There's still some functionality that needs to be worked out, but it's coming up. And this is where your storage applications are going to start seeing more and more use. So in talking with a lot of customers and looking at the market, we've established a couple of use cases for containerized storage and for container volumes specifically. The first major use case is what we call the unshared volumes. What this means is that one volume is mounted to a single container host, whether that container host is virtual or physical. And only the containers within that host can access the volume. And really, it's really more one-to-one, that at any given time, only one container is really accessing that volume. So very similar to today when you mount a virtual disk on a single VM, and only that virtual disk and its applications can see, only that VM's applications can see the virtual disk. So that's the first use case. And what you might actually see for that is something like running a container-based SQL or NoSQL database attached to a single container microservice or application. And from what we've seen, this is the most common use case that people are trying to solve. But if you imagine that containers can be, at scale, can run across an entire cluster of hosts or even farther, you might begin to see that people want to have your storage shared across multiple hosts. So let's say you're running something like a Kubernetes cluster, and it has a master and slave nodes, and it has several containers for co-located applications that need to access the same set of data. Perhaps it's a set of dev tools, or it's a set of static content like logos, pictures, et cetera, across all of your application instances. For this use case, you're really going to want a type of storage which is distributed, so similar to a distributed file system, where all the containers can read the same directory. Maybe only one container can write to a single file at a time, but at least for read-only purposes, everyone's going to need to see the same thing. And this becomes really important when you have containers moving around, getting killed, restarting on a new host. Somehow your storage needs to keep track of everything and needs to be connected to all of these container hosts at once. So we think that's an important future use case as containers move more into a production world. And the final use case is actually really the original containerized storage use case, and that's where you persist to some sort of external storage using a RESTful API. This could be an object store for retention archival. It could be a database as a service for configuration, transactions, et cetera. And we pointed out the advantages and disadvantages of this method. It is important to know that this could be in a public cloud, so it could be something like vCloud Air, or it could be within a private cloud, like an OpenStack, OpenStack Swift object store, for example. So both use cases are viable. So how does containerized storage really work in practice? There's a number of ways people have done this. And really, if you talk to any number of customers, you'll find many different ways for running containerized storage. But from what we've seen, this seems to be the most popular and straightforward method. So you have some kind of application orchestrator, such as Kubernetes, Mesos, Docker Swarm, et cetera, that is really scheduling individual microservices. And each of these microservices are independent, but they are talking to each other via RESTful API. And that's how they coordinate. And each microservice can consist of a series of stateless and stateful containers. So this is just a really simple example where a given microservice might contain one compute-centric container, such as an API front end. It'll contain another container which contains a database engine, so MongoDB, Cassandra, MySQL, something like that, that's running the actual logic for the database. And then all of the actual data and transactions is persisted out to some external storage. And again, that external storage could be a local host storage, but more likely you're going to want to be putting this on some kind of external storage platform in order to take advantage of the data services, snapshots, clones, et cetera, replication of that storage platform. So this is the model that we're starting to see more and more works in a production-capable environment. Now, you might be, and I've actually mentioned this a couple of times, so maybe I'm spoiling the punchline, but you might have noticed that container volumes and virtual disks sound and look really familiar, right? A VMDK can store all of your necessary data. It sits on a data store. You can do things like snapshots to it. Container volumes are a directory on a host. It contains all your stateful data. You might be able to do things like snapshots and clones on it. So shouldn't we be able to just make container volumes work in the same fashion as a virtual disk? Wouldn't that be great? And of course, setting up the punchline. This is where we're announcing our vSphere driver for Flocker 1.0. Flocker is an open source software that allows you to manage and coordinate your containerized storage applications. So I probably can't describe it as best as some other people in the room can, so I'm going to bring up the CTO of Cluster HQ, Luke Marsden, who's going to talk a little bit about what it is that Flocker does and how it works. And then I'll go back and talk to you about how the vSphere integration with Flocker works. So
perfect.
Yeah.
Thank you, Vivek. Well, it's great to be on stage and able to talk about the work that Vivek and his team have been doing with us at Cluster HQ. We have been working hard on getting Flocker, which is a container data manager, integrated with vSphere, which means that it's now possible to run stateful containerized applications on the VMware stack. So I'm just going to quickly talk a little bit about the problem that Flocker solves. So in the diagram at the top here, we have sort of what happens when you just use native Docker today. With Docker volume, well, Docker best practices suggest that if you have a stateful application, like a database, then what you're supposed to do is you're supposed to allocate a volume and attach that volume to the container. The problem that occurs there is that with just regular Docker, a Docker volume is just a directory on the host. So if you have a virtual machine that has multiple containers on it, and each of those containers has a Docker volume, then as soon as you try and move that container from one machine to another, the data gets left behind. So in this diagram here, the data volume is literally just a directory on the host. And if you try and start that container on a different machine or a different VM, then the data isn't there. So your database starts up and it's empty, and then everyone is sad. With Flocker, however, we've made it possible to move containers and data together as an atomic unit. That means that you can relocate a container from one VM to another. Maybe you start out by putting 100 containers on one VM, and then your VM starts getting a bit too busy. So you're able to provision another VM and then move some of those containers with their data around. So it's really useful for important operational use cases that come up when you want to run containers in production. So I'm going to talk a little bit about, let's go to the next level of detail on the architecture. So this is how Flocker works with an arbitrary shared storage backend. The Flocker API or CLI is how users interact with the system. So they might say, create me a container or create me a volume, and please put it on this host. That goes through to the control service. There are two hosts then in this example. And to begin with, there are two containers running on the first host. So just like the example I just gave, suppose we've got two MySQL databases running on host 1. And then host 1 starts getting a bit busy, and we decide that we want to move container C2 onto host 2. So because what Flocker does is it's created this link between the V1 and the S1 and the V2 and the S2, basically it's allocating these volumes not as directories on the host, but actually going down to the underlying storage, the vSphere storage in this case, and attaching that storage to that container. It means that when you move that container, Flocker manages detaching that volume from host 1 and attaching that volume to host 2. So it means that you get complete freedom in where you run your containers within your vSphere cluster, and it makes it possible to move things around, which is critical to run things in production. So I'm not going to talk much more about this. I'm going to hand back over to Vivek for a demo in a minute. So this is my last slide. I just wanted to give some context for Cluster HQ and where we're going with the Flocker product. So apologies for all the words on this slide, but basically the diagram on the right describes it best. Cluster HQ is connecting the storage universe with the container universe. We want to make it possible for you to use whichever container tools you like best. You might want Docker Swarm, which has a great developer experience. You might want to use vSphere, which is in production at Twitter and Airbnb. Or you might want to use Kubernetes from Google. You might want to run on CoreOS. You might want to run on Ubuntu or CentOS or even Photon. And so Cluster HQ gives you complete freedom over choosing those tools because we've integrated with all of them. And by the way, it's difficult to run stateful workloads with these tools without Flocker because of the problem I described before. And we're also integrating downwards into all of the different storage stacks. So we're really excited to announce the vSphere driver because it works with vSAN and, in fact, with any VMware storage, I think.
Yeah, we'll go over some of those details.
Yep.
Yeah.
And we are also growing our partner network. We support OpenStack Cinder as well for people who are using OpenStack. And we also integrate with public cloud storage backends. And then looking to the future, we're planning on adding a depth of storage capabilities. So this is just the beginning. This just allows you to do the basic thing that you want to do of running stateful containers in production. And then there's clearly a wealth of other things you might want to do with your container data volumes once you've got them running, like back them up, restore them, move them around, and possibly even move them between clouds and between hybrid environments, like from vCloud Air to your vSphere and back. So with that, I just want to get a quick show of hands. So who here is using vSphere? First up? Cool, OK. Who here is interested in containers and microservices? OK, great. You come to the right talk. So finally, who here is interested in trying this? OK, cool. So for everyone who's interested in trying it, please pull out your cell phone and write me a one-word email and just say, hey, I'm interested in trying this. Because what I really want to get out of this session is to connect with some of you and find out what your use cases is. You find out what your use cases are. Find out what you want from this sort of solution. And yeah, I'd gladly offer up a half hour or hour of my time to get you started with a demo as well. So with that in mind, oh yeah, follow us on Twitter as well at ClusterHQ. With that in mind, I'll pass back over to Vivek, and I think you've got some really cool demos for us.
Yeah, thank you, Luke.
Thank you, Vivek.
So I want to re-ask that question. How many of you are interested in trying this knowing that it's free? So a couple of details on the vSphere driver for Flocker. So again, the use case is really running containerized stateful apps on your current vSphere deployment using the open source Flocker software. And it's about being able to move both the containers and the data volumes from one ESX VM on your deployment to another. So this is compatible with all vSphere storage backends, so vSAN, vVol, VMFS, NFS. It's a pretty straightforward install, configure, deploy process. And importantly, it's free. You can pick up the driver at our VMware GitHub page, github.com/VMware/vSphere-Flocker-driver. And just like Luke, the goal of the Storage for Cloud Native Applications initiative is to really connect vSphere, to connect the VMware environment, the IT environment, and the cloud native developers environments all together. And so we really want this to be a conversation. We're starting to work on a lot of projects which will bring us more into the open source world, which will connect us more with the different types of container tools that you're interested in running. So give it a try, download the driver, leave some comments, leave some feedback. We'd be happy to take them. We want to keep making more and more improvements. And as you'll see soon, we've got a lot of other cool stuff that we're working on in this area as well. So. Oh, and just a quick piece of how this actually works architecture-wise in vSphere. So again, if you're running native Docker on vSphere today, you can create a container volume on the local VMDK for a given VM. So right now, let's assume that there's a containerized database application, maybe it's MySQL, that's running on ESX VM1, and then the VMDK1 that's attached to that VM1 will contain the container volume. However, as soon as you move that container database app to VM2, you've now lost your container volume because it's still sitting back on VMDK1. So your database starts without any of its old data, and someone's going to yell at you. Now, if you're running vSphere with Flocker, instead, it creates a separate VMDK which contains the container volume. And this is stored in a specific folder that you tag on your data store. So you'll tag a data store to be your Flocker data store, and you could tag multiple data stores to do this. And then all the VMDKs will sit within that within that folder on that data store. And then whenever you call using the Flocker or Docker API to create this container volume or to restart the application and move it somewhere else, in the back end, vSphere takes care of all the details, and the driver makes sure that your container volume is moved from ESX VM1 to ESX VM2. So it's a pretty straightforward process, but it allows you to really start running these containerized database applications. So I promised you some demos, so I'll show you some demos. This is a demo that is showing a configuration and deployment of a containerized MySQL database app on a vSAN data store. So, and I've got a couple of captions to make it a little easier to follow, but I'll be running through the explanations as we go. So right at the beginning, you can see in the web client that we have a vSAN cluster. I apologize that it's kind of small text, but this is a vSAN cluster with 3 VMs right now, Flocker Node 1, Flocker Node 2, and Flocker Node 3. And these VMs are all sitting on the same vSAN data store. And we're going to actually go into the data store browser so you can see the folder. Within the vSAN data store browser, we've created a folder called Flocker. And this is how you tell Flocker where you're going to actually be storing the VMDKs. So right now, there's nothing really in here because we haven't created any container volumes yet. We actually moved to the, I'm going to pause this for a quick second. We moved to the CLI now. And in order to create a containerized database application, you have to create a YAML file, so just a configuration file that gives the details of that database. So right now, this is a MySQL volume, and this is going to move a little fast. This is where the mount point that it's telling you where we need to go, so /var/lib/MySQL. And in particular, you label some of the details around the size as well. So this is going to be like a 4 gigabyte database right now. So right now what we're doing is deploying this MySQL database on node 1. So remember we had Flocker Node 1, Flocker Node 2, Flocker Node 3. So you use that YAML file to configure and tell Flocker that, OK, I'm going to actually put this on Flocker Node -1. And then you make a simple API call to that particular VM running this configuration file and say, OK, give me a MySQL file. So it takes only a couple of seconds to get a Docker file here. Now notice here, you'll see that there's a new VMDK that's been created. This VMDK is where that container volume is sitting. So it's already been created on the vSAN data store. And remember that now that this is available on the back end, you can start doing things with this VMDK if you choose to do so. So you could theoretically attach it to a VM and take a snapshot on the back end. You could start putting storage policy-based management on this. And we're looking at being able to develop that within the API as well. Now we go back to the CLI, and we call a couple of Docker PS commands to wait to see. And now you can see, oh, hey, look, we now have a MySQL database. Now, just having a database doesn't mean a whole lot. We want to be actually able to add some information to this database, some actual data, if you will. And we want to make sure that any data that we keep, if we move that from node 1 to node 2, VM1 to VM2, that the data itself is kept. This is moving a little bit quickly, but you're creating just a random table, and we'll put some random amount of test values into it. So we'll just call it Flocker test. And then the goal then you see is well, I hope this works because it's a recorded demo, that when the container moves from VM1 to VM2, that your data stays with it. So right now we've created a single row that just says Flocker test. And then we quit the application, and we're going to try to move it out into a new VM. OK. So now to move the MySQL app to node 2, you're going to go back to the Flocker API. You need to put in a new YAML file, a new configuration file that says, OK, please move this to Flocker node 2. So now we're looking at the new configuration file, and you'll notice that we've changed it to the second one. This is the other IP address for the second VM. So OK, we go back to Flocker-deploy. This is the Flocker API. And we're now moving it to MySQL node 2. Now, on the back end, nothing is changing in this case from the VMDK's perspective. It's still sitting on a vSAN data store. But behind the scenes, it's connecting that VMDK to the second VM that we requisitioned. So this is a shared storage backend that Luke was referring to in the past. And I'd be remiss if I didn't say that we think that vSAN is, of course, the best way to run these things. Sorry, I have to do that as part of my job. So we're calling Docker PS now. We're trying to see has the new container been created? Because remember, when you're moving a container, what you're really doing is killing the old container and starting a new one, because it starts very quickly. So I think it already happened. Up 7 seconds, you see right there. That's the new container. Now we want to see, is our data preserved? Here's the moment of truth. This will probably take longer than it should, but you will find, in fact, that your database, there's your MySQL application, and I'm just going to skip ahead to the punchline. Hey, look, select star from test data. The data's there, Flocker test. Hey, it worked, everybody. So that's just a quick demo of that functionality. And actually, this demo is available on YouTube. I have a blog post up talking about sort of the mission of storage for cloud-native applications and a little bit about the Flocker demo. So you can take a look at it on YouTube. It's available. And it has captions, so it explains what's going on. As I mentioned before, I'd be remiss if I didn't say that we think Virtual SAN is a great way to run your containerized database applications. So in case you're unfamiliar with Virtual SAN, it's a software-defined storage platform optimized for VMs. Hypervisor converged architecture, so your VMs and your storage are sitting in the same clustered hardware. Runs on any standard x86 servers. It's a series of nodes for a clustered data storage. Pools all of your hard disk drives and your SSDs, and we now have an all-flash model, into a shared data store that delivers enterprise-level scalability and performance. And importantly, the ability to manage per VM and per container storage policies. This is something we really want to do. Be able to apply data services for your storage-related data services to specific containers and container data volumes. And the idea here is that your average developer probably doesn't want to care what all those underlying storage details are. They just know that this app is mission critical, this one is test dev. Give me the data services that I need to make sure that my app gets what it needs. And that's the idea behind doing these storage policies, is that to the app owner or the developer, you just say, OK, this is a mission-critical policy. This is a test dev policy. And the VI and storage admins below can tell the infrastructure what that actually means from a failures to tolerate or a resiliency perspective. And of course, this is very deeply integrated with a VMware stack. But don't take my word for it that vSAN is the best way to run containerized database applications. We actually had a customer. Their name is Holiday Check. They provide vacation reviews and rentals over in Europe. And they actually came to us, the two of our companies, and said, hey, is there a way to get this Flocker working on Virtual SAN? So we really worked early with them as a design partner to understand what the needs of the customer would be. And they came back, they liked what they saw, and they gave us this quote. So I would encourage you to give this a try. We are very proud of what we've done with Cluster HQ, and we'd like you to test it out and see what you think too. So stepping away from what's available now, so that everything that you just saw is available now and works today, I want to talk a little bit about what's going on in the future. And of course, this means I'm not going to give you any specific release dates or give any specific feature promises. But these are sort of the things that we're really trying to look at in the future of software-defined storage for cloud-native applications and for containers. So you probably heard the announcements around vSphere integrated containers earlier this week. It's a solution that allows you to run containers as a one-to-one container within a very small VM, very small and fast-moving VM, which allows your developers to get all the benefits that they want from containers: fast deployment, easy application provisioning and packaging, the use of a Docker API or other container APIs, but provides your IT admins with the ability to see these containers as individual mini VMs and apply all the same features from vSphere that they were able to apply to those to containers now, that they were to apply to VMs. So from a storage perspective, we're making container volumes work as a part of vSphere integrated containers. I think there was a demo shown in a previous session that actually showed a container volume being deployed on a vSAN data store using vSphere integrated containers. So expect to be able to use all the same features that you've done on vSphere for your we're using vSphere integrated containers, and that's coming in tech preview now and looking at a release more towards next year. And of course, this won't require any rebuilding or re-architecture. You also may have heard some of our announcements around Photon platforms. So this is a new distributed architecture for running high-scale, rapid provisioning of container-based applications. And you can rest assured that we are looking at the best ways to bring the benefits of software-defined storage and all the things that we've talked about to the Photon platform. And if that's something you want to talk about, we can talk about it under more of an NDA session. So I'd happy to have a one-on-one conversation. So you can bring that up with your TAMs or with your accounts and come reach out to me. But in general, what are sort of the trends that we're looking to build when it's the future of storage in a cloud-native world? Now, as we said, cloud-native is about being built for scale, and it's about decoupling as much as decoupling your actual application processes from the underlying infrastructure. What this means is that you really need to have a distributed infrastructure. You really need to be able to see a view of multiple clusters in order to keep track of this huge scale. And importantly, your storage needs to be able to keep up with the compute. So anytime there's a storage problem, and we all know that storage problems are difficult ones to solve, and that anything that relies on physical data takes a lot longer to solve and requires a lot more protection and care and feeding. So what we want is really global management, being able to take a bird's eye view and having something that's very automation friendly, that scales very quickly. But we also want scalable troubleshooting. We want to be able to see if an individual drive is failing, you can zoom right into that individual drive, see what's going on, see if there's any problems. But then zoom back out and see cluster level, are you having any capacity issues? Are you having any I/O planning issues? So really it's about decentralized analytics, it's about information gathering, processing, and prediction. And then from a usability standpoint, in a cloud-native world, and I'll keep telling this again and again, we really want this dual focus on both IT friendliness and developer friendliness. From an IT perspective, you want GUI or scripting that gives you infrastructure operations. And from a developer perspective, you want APIs and CLIs that allow you to do easy app integration. But if you remember earlier on, I talked about that shared volumes use case, right? What if you had several containers in different hosts that you really wanted to be able to see the same storage? As you're spinning up tons of these containers, you're going to want to make sure that any of your stored data has to be able to keep up with those containers. You need to be able to share it among multiple hosts, but importantly, if you need to do things like clones and snaps, you need to be able to do them very, very quickly in order to keep up with the container provisioning and scheduling. So one of the things that we're kicking around is a distributed file system. Now it's a little too late, I think, to check the show floor now, but if you visited the office of the CTO booth, we had some examples of this. So we're working on this virtual distributed file system, which is a scale-out file system built on top of a hyper-converged storage backend. So you can think of this as like a scale-out distributed file system that sits on top of vSAN and provides you with a POSIX file system. Now remember, we said that most developers really like writing to a local file system. So giving that local Linux file system and offering really cloud scale file sharing across all of your hosts and cloud scale cloning and snapshots. So the ability to spin up new copies of your files as fast as your containers are able to actually see them. And also to have per file and directory access control and security, because in a production environment, knowing who is accessing which of your files is extremely important. And the main thing, again, to reemphasize, aside from the sharing aspect, is really like order constant runtime snapshot and clone creation. Again, it's about making sure that your data is able to keep up with the stateless containers compute applications. So in an earlier session this week, one of my colleagues, Rawlinson Rivera, just built up a really quick demo that shows how this works in practice. Let me see if I can get this working. Now, this is very simple, but the idea here is we're trying to show, can you really get that scale that we were talking about when it comes to cloning files and snapshots, so that, again, your data can keep up with the containers. So right now, and I hope this is running correctly. There we go. So right now, you notice that he's cloning 2,000 files. And I don't know if you noticed, but it said done. Those 2,000 files that were cloned using the distributed file system were done in less than a second. An instant clone. Let me just quickly show that again in case that was hard to see. Clone, 2,000 files, done. Now these are a bunch of QuickTime videos. They're not small. This took 0.032 seconds, so less than a second. Here's all the movie files that were cloned. We were able to clone files using this distributed file system at an astounding rate, and we're able to share them with all the hosts that are in that given cluster. So any containers that could be on those hosts could see them. Now, what actually is this video? Well, I'll just skip ahead to that too, because Rawlinson's a bit of a clown. This is him skateboarding in a skate park. It's the same video about 2,000 times. This is punching clouds in case you keep up with him on Twitter. But again, what did we just see? We just saw a single file, a single movie file that was cloned in less than a second 2,000 times, and that was shared among all hosts that are in that cluster. This is really what we're trying to build as a future of software-defined storage for containers. We want something that all containers should be able to access at any given time, and to make sure that the data is secure and visible to the right players, and that it's cloned and snapshotted at a very quick rate. Yeah, let's talk about that. We can talk about that afterwards. But let me get back. So that's a demo of what we're working on. You know, this is still very much a research project. I should be clear, but it's some of the cool things going on within VMware right now. Oh, well, that was a demo. All right, so quick overview. So what's now? The vSphere driver for Flocker 1.0 is available now for free. Again, this is the GitHub page you can download it at. Please give it a try. Let us know what you think. Let Luke and the rest of Cluster HQ know what you think. We're working on extending this functionality. So as he mentioned, being able to bring this data services of the storage platform directly to the container API and the CLI. That's some of the things that we're looking to develop with this. And what's next? Really, we're looking for integration with things like vSphere integrated containers, Photon platform, and our other cloud-native applications processes. And also just more open source and open projects that allow us to interface with developers in the community. And in particular, I'd love if you guys would reach out to me. You can follow me or direct message me at Twitter at the vSaraswat. I'm the head for storage for cloud-native applications at VMware. I would love to talk to more customers about some of these things, and especially in an NDA session, I can talk about things a little more freely. So that's really the end of my session. I'm happy to take, Luke and I will both be happy to take questions. And thank you guys for staying all the way through the end of VMworld. Appreciate having you.